Great. Please get started. Thank you.
Okay, so thank you for inviting me, and I'm very pleased to join the post-scientific grant. I'm going to talk about coupling-based particle smoother with application to diffusion. So this is the structure of the talk. I only have about 30 minutes, so I don't think I will have the time to cover everything. Let's start with the problem formulation. So we are in the case of state-based model. H0 HT is an unobserved and possibly non-homogeneous Markov process. Then you have Y0 and YT, which are observations that are, well, conditionally independent given the X. So the typical case is, well, when YT is just a noisy observation HT, right? So for the sake of notation, I use here H0T, which is a shorthand for H0 until HT. And let MT HT minus 1 DHT be the Markov transition from HT minus 1 to HT, and the probability density, for instance, with respect to the Lebesgue measure, is denoted by this. So you have this is some small m, and this is the capital M. All right. By the way, if you have any questions, then do not hesitate to interrupt me. So here are some examples of this model. For instance, you have IC, which is the position of the car, and YT is the noisy measurement with GPS, for instance. You can also have IC, which is the market volatility, and YT given IC is the log return. So IC here, you see, it's just a stationary process, and YT given IC is a certain observation defined on IC. The third case is more interesting, where you have IC, a stochastic process, and Y0T is not the observation at discrete time. So the goal is to simulate H0T given the observation, right? This is a mood thing. This is more difficult than the filtering task, which is just to find HT given Y0T. Okay, and here's the difference in the second example here. You see that the density transition between HT minus 1 and XT is calculable, right? It's just a Gaussian stuff. Whereas in the third case, the density is intractable, but the dynamics can still be simulated, for instance, using Euler discretization. Right. So this talk is largely based on our recent preprint with Nicolas Chopin. So there are two parts in this. We develop fast strategies to perform smoothing in models with tractable densities first, and then we propose a novel algorithm to deal with intractable densities. So I will focus more on the second part, but I will have to review the first part so as to make the notations coherent and to give a complete introduction to the topic. So yes, so now I will go over some basic concepts on particle filtering and smoothing. Some of you are familiar with this, some may not, but I hope that this will give you some ideas of how it works and what are the problems, what are the computational and theoretical problems underlying these concepts. Right. So in both cases, the distribution of IC given Y0T is intractable. There is no analytic expression for mean, variance, quantile, and so on. So you have to approximate it in the Monte Carlo way, which means that you approximate that distribution by sum of weighted direct masses. For instance, if you approximate the distribution of HT given Y0T by this sum of direct mass, which means in terms of function approximation, when you have an integral, you can write it in this form, right? So it's just the sum of the function, the test function H, evaluated on the particles, and you weight them appropriately. So the question is obviously how to produce the weight WT1 to N and the particles the HT1 to N. Okay, so this slide contains some heavy notations, but actually these notations will be used over and over again during the talk. So I will stress on some of the notations that will be important in the next slide. So at the time T minus 1, you have this distribution, which is the conditional distribution of your hidden state at the time t-1, given your observation until time t-1, and this is approximated by, well, a somewhat direct method at time t-1. So you have w-t-1i direct of x-t-1i, and this is the input of your algorithm. What you do, you first resample, you select the indices AT1, ATN, conditionally IID from one end with the weight. Okay, so now you have another approximation of your same distribution, but the weights here have disappeared and they are replaced by 1/n because you have done the resampling step. Then you do the move step, in which you will simulate HTI given your resample particles. So your resample particle is HT-1 ATI, where ATI are the ancestor indexes that you have resampled in the previous step, right? So you simulate that for each I equal to 1 or n, where capital N is the number of particles that you choose. And so now, so in this step, at this step, you have an approximation of the filter distribution of HT-1, and now you go to an approximation of HT given Y0T-1 because you have done a Markov move step, right? And then you reweight it. So you set WTI is equal to the likelihood of your observation YT given HTI, and then you normalize the weight such that the sum equal 1. Well, why we do this? You can decompose the distribution at HT given Y0T as the distribution given HT or HT given Y0T-1 times the likelihood. And so here you have an approximation of this term right here, and you multiply the likelihood, and that's why at the end this direct sum WTI direct HTI is an approximation of the distribution of HT given Y0T. Okay, so at the input you have an approximation of the filtering distribution at time t-1. At the output you have an approximation at time t, and you continue like that until the end. So there is a genetic interpretation of this algorithm. You can think of resampling as a selection step and move as a mutation step. And so HTI has been created by this operation, and it's natural to say that HT-1 ATI is the ancestor of HTI in the particle filter. And HT-1 ATI in turn has its own ancestor too, and so on, and you can track everything back into time 0. So if you track everything back into time 0, then it can be proved, and it is well known in the particle filter literature, that the setup trajectory HT-1, HT-n approximates the smoothing distribution, which is the distribution of your observation, your hidden state given the observation. So the question is, it is a good approximation. Well, if you are familiar with particle filter, you know that this is not the case because you have the population degeneracy at time 0, where you have a fixed population of psi n, which evolves from one generation to another, and at each generation, each individual choose one ancestor from generation t-1, and after some iterations, all individuals at time t have the same ancestor at time 0. So this is a very well-known phenomenon even outside the particle filter literature. So you may have heard about White-Fisher model or genetic drift and things like that. Okay, so to prevent this, in the particle filter literature, a method called forward filtering backward smoothing has been proposed. So the idea is very simple. Well, if you look at this graph, which describes the relations between your particles and your variables, you see that the distribution of HT-1 given Y0T and HT can be decomposed in that form. Here the filtering distribution, and here is the Markov transition kernel. So Okay, I'll go a little bit quickly over this because I think if you're familiar with particle filters and you know that we have algorithm. So here's the loop. At time t, you sample IT, and then you sample back at every step using this weight. And these weights are nothing other than an empirical approximation of this product, right? So at each time, once you have the index IT, you sample the index IT minus 1 according to the weight WT minus 1I and MT HT minus 1 HTI. And at the end, you have a trajectory that approximates your smoothing distribution. And the complexity of this stuff is ON squared. Okay, so one of our contribution is to lower this complexity to linear for trackable models. So I only use one slide for this because I want to come faster to the part of intractable models. So instead of doing a full sampling, you can use an MTNC step. So you can start with the ancestor. Once you have the index IT, and when you sample from IT minus 1, normally the ancestor is not taken into account. But here you can take it into account. You can set IT minus 1 being either the ancestor of HTIT or another proposal from the weight distribution at time t minus 1, and you accept or reject it with, the Metropolit-Hessing ratio, and you can prove that this leads to an algorithm that's stable as t tends to infinity, and you can also extend it to the online smoothing case. Okay, so let's come to intractable model, a diffusion case. So you have to be able to calculate the transition density, otherwise you cannot do backward sampling, right? In many situations, the MT HT minus 1 HT is unknown. For instance, you have diffusions like this. You can simulate it using Euler discretization, for instance, but still the transition density is intractable. So what you could do is the following. You can say that what happens if your particle has more than one ancestor right from the forward path? And in that case, explicit backward sampling may not be necessary, and you can do this using coupling. So traditionally, the Markov mutation step is performed by, simulating conditionally independently on the particles selected through the resampling step. So instead, what you can do, you can consider two resample particles, HT minus 1 and HT minus 1 prime at time t minus 1, and then you simulate HT and HT prime according to the transition kernel, but not independently. You do it in a way to increase as much as possible the probability that HT equals HT prime. And so if the coupling is successful, then HT automatically has two ancestors, HT minus 1 and HT minus 1 prime, as time t minus 1 without needing any backward sampling. And so just go a little bit quick over this. So you can do it in a more formal word. So at time t minus 1, you have the particles, you wait, you draw 2n ancestor particles, you simulate the HTI1 and HTI2 from the coupling of the two measures. So if the coupling is successful, then you can say that HTI is the two parent particle, and otherwise you can say that HTI is a one parent particle. And when you do the backward sampling, what you can do is that, well, first you choose HT from the final population with the weight WT1, WTN, and then given HT, so here's a small t because you're going backward. If HT is the two parent particle, you can select randomly one of the two parents, HT minus 1. And if HT is the one parent particle, you just set HT minus 1 to its parent, right? So now you have a smoothing algorithm that is conversion, and under appropriate assumptions like strong mixing and coupling of reasonable quality, you have an algorithm that is stable, and the time t tends to infinity, and the complexity is linear. So I mean, even when the model is even when the model is tractable, you can still use this algorithm to to get a ON complexity smoothing algorithm. All right, so now let's come back to diffusions. So here you have the reflection coupling of two Brownian motions. So many of you are familiar with this, I think. So here you have two correlated Brownian motions starting from 1 and -1, and the noise is asymmetric through the dash reflection plane. Okay, and it couples after a finite time. Well, you can extend this to the case of two diffusions. So if you have two diffusions, the HTA and the HTB, which have the same dynamics, but which start at different points, then if you correlate the two Brownian motions by this formula, which is just an extension of what you have seen here to higher dimensions with different sigma, then under regularity conditions, you have a finite time tau such that H tau A equals H tau B. Okay, so that's great. But, well, how to simulate this? If you do it by discretization, then you know that there is zero probability that the coupling time is going to be exactly k times delta, where k is the integral number and delta is the discretization step, right? So you know that, well, in theory, you have a finite time tau such that the two are equal, but in practice, simulating it is not easy. So we propose a modified version of this coupling so as to have finite meeting time for the discretized diffusions. So it's quite surprising that, well, this construction has been proposed in the literature in 1986, but simulating couplings of two diffusions is, well, at least in my knowledge, overlooked in the literature. And the cause, I think, is that coupling until now has been mostly a theoretical tool, and it hasn't been really used as a simulation technique until the article of Jacob on unbiased and CNC with coupling. All right, so how do we couple this? Well, if you want to simulate this by Euler discretization, for example, then it just boils down to coupling these two measures, right? So coupling to Gaussian distribution. Okay, so I will simplify the notation a little bit, and I say that, okay, I want to couple two Gaussian distribution with, the first one is with mean mu1, and the covariance matrix K1, K1T, and the second one has mean mu2 and covariance matrix K2, K2 transpose. Okay, so first I will cover rapidly three solutions that are unsatisfactory, and then I will give our solution for this. So the first one is a reflection coupling, which I have shown you before. So you simulate that one from a standard normal. That two is a reflection of that one through an appropriately defined plane, and then you have H1 and H2, which are defined naturally. So the good part of this is that you have good theoretical properties. If you use it for your discretization, then it can bring two far away trajectories together. The problem is that you have a zero coupling probability at each step. Then you have the maximum coupling, which is very familiar. While simulating from a distribution is equivalent to simulating from the uniform distribution on the set underneath the density curve, right? So the set R1 underneath the density curve is given here. So it's a couple of H and S, where H is in the space of your distribution, and S is a real number that runs from 0 to the density. So N H mu1 K1 transpose is a normal density, the multivariate normal density at point X and with parameters mu1 and K1 transpose. Okay, so the problem now becomes the coupling of two uniform distributions on R1 and R2. So you can look at this Venn diagram. which gives you some intuition about this. So first, you can simulate y1 uniformly in the first set R1, and then if y1 is in the intersection of the two, then you can simply set y2 equal to y1. Otherwise, you will need to simulate y2 uniformly over the difference between R2 and R1. And this stuff really takes, cannot be done in an obvious way, because, well, the only obvious way to do it is that you simulate independently, you simulate uniformly on R2, and then you wait until your Y2 gets out of the intersection. So it has a random execution time, and when R1 and R2 are close together, then it can take really a long time before your simulation finishes. So that's the downside of maximal coupling. Okay, and there is a reflection maximal coupling, which has been proposed to solve this problem. So to do reflection maximal coupling, you have to assume that your K1 equal to K2, where K1, K2 are the parameters of the two normal distributions that you want to simulate, that you want to couple. Right. So if you have K1 equal to K2, then what you can do is that, okay, you simulate Y1 uniformly in R1, and if Y1 gets into the intersection, well, then you will set Y2 equal to Y1 as before. Otherwise, you will set Y2 to H2S, where S is the same real number as here, where H2 is obtained through H1 via the reflection coupling. So the advantage of this is that you have finite execution time, you have non-zero coupling probability, you have good theoretical properties, but, well, it's only applicable in the case where K1 is equal to K2. And to get that, you really have to work with diffusions with a constant sigma term, which is, well, which makes the whole thing a lot less interesting, actually. Okay, so I have a question in the chat or something. Okay, 5 minutes. Right. Okay, I think I only have 2 minutes. Okay. Okay, anyway, yes, so 2 minutes, I try to finish it rapidly. So our coupling is a new coupling that behaves like the reflection coupling when the two trajectories are far away, and like the maximum coupling when they are close. So the idea is that, okay, you simulate according to the reflection coupling, you simulate another uniform variable, which can be assigned to Z under certain conditions. Okay, so I do not have the time to go through this. I think it's very easy to understand, but I answer it in the question part if you are interested in that. So let's come to my last slide, which shows how it works in practice. So you have, okay, we try to work with a non-carbon-terrace stochastic differential equation. So here are the equations. Here is a plot of the hidden state and the variables. And, well, in this case, you can see that our smoothing algorithm works very well, whereas the general tracking smoothing algorithm has a lot of degeneration at time 0. Okay, so thank you for your attention.